The Higgs boson might get better press, but astrophysicist Ray Jayawardhana says neutrinos are the particles people should be paying attention to. So, joining us now to tell us more about these elusive particles is Ray Jayawardhana. Hello, welcome back to the agenda.
Nice to be here, Piya.
Okay, I'm going to ask you the most obvious question first. What the heck is a neutrino?
A neutrino is a type of elementary particle with a rather quirky, if not bizarre, characteristics, personality. There are tons and tons of neutrinos all around us. In fact, it's the most common matter particle in the universe.
Like right now, it's
right now, there are
everywhere in this room.
Trillions of neutrinos passing through your body every second of every day. Many of them coming from the nuclear furnace at the heart of the sun, others produced in the upper atmosphere of the Earth when cosmic rays interact with atoms up there, and some produced actually right beneath our feet by radioactive decay of elements in the Earth's interior.
What's their job?
Well, they're essential constituent of matter. The subatomic world is rather intriguing and is full of all these different kinds of particles. Neutrinos, as I said, are the most common type of matter particle, and they're incredibly low in mass, and they hardly ever interact with anything, which makes them very, very difficult to pin down. Okay,
we talked about in the introduction there, everyone knows about Higgs boson now. Is the neutrino related to that at all?
Well, it's all the Higgs boson is part of what's called the standard model of particle physics, and the neutrino is also part of that theoretical framework for sure. The neutrino was actually first invented, in a sense, or proposed as a hypothetical particle back in 1930 by a brash young physicist by the name of Wolfgang Pauli to account for some energy that seemed to go missing during radioactive decay, a particular type of radioactive decay, beta decay, where scientists were puzzled for many years as to what's happening. And he came up with the solution, well, maybe it's a particle we don't know about yet. And it took 25 years since that initial proposal for the neutrino to be detected experimentally.
So that's in the mid-50s?
That's in the mid-50s. That just gives you a sense of how difficult it is to detect it, to measure its properties, because it hardly ever interacts with anything. These neutrinos pass right through our bodies, which is a good thing. They leave no trace and cause no harm, but they also travel right through the Earth itself. It's only every once in a while a neutrino would interact with a nucleus of an atom or an electron, and that's how we could confirm their existence.
Okay, if these things, I know you say it take a long time from it first being discovered to actually attaching other characteristics to it, but that's in the mid-50s. We're now in 2014. I've never heard of a neutrino till I picked up your book. You seem surprised. You think people have heard of neutrinos?
Absolutely, yeah.
Really?
Well, I mean, I wrote
in your world of as an astrophysicist, maybe, but I don't think the guy on the
street. Do you watch The Big Bang Theory?
I don't, so okay, I guess that's my problem.
The number of neutrino jokes, or the number of times on that whiteboard in the background of the show that neutrino properties are described, is surprising. It's everywhere. It's certainly part of pop culture, and I should say that there've been tons of neutrino jokes, and a few years ago there was this brouhaha because of a report that neutrinos may travel faster than the speed of light, and then it made front page headlines everywhere in the world, including right here in Toronto.
Clearly I was asleep that day. Okay, but let me ask you this, because I'm going to dollar for dollar bet you that more people would know about Higgs boson than neutrino, and I would argue that your little particle that you're so fascinated with suffers a bit of a PR problem.
It certainly does, and the fact that the Higgs boson was dubbed the God particle certainly helped its media profile, if nothing else. But I challenge you that it's so much harder to explain and understand the Higgs boson than it is to make sense of the neutrino in many ways. You have to really appeal to rather elaborate concepts of quantum field theory to make any sense of the Higgs boson.
Okay, but it still suffers a PR problem.
For sure,
okay.
Absolutely.
We have to resolve that, apparently.
Yeah. So I wrote an op-ed in the New York Times in December where I basically pitted the two particles in a somewhat humorous way and made the case for the neutrino, that it's really worthy of our attention.
Okay, well, we're going to make that case as we carry on our conversation. But you talked about how these things are always passing through us. They rarely interact with anything else. How do you, as a scientist, detect a neutrino then?
So you have to measure them on those rare occasions that they do interact. What that means is that scientists have to build incredibly large volume detectors. So the story of the neutrino that's in my book, The Neutrino Hunters, is a story of science, but it's also the story of the people doing the science, their colorful personalities, and also even the great extents that they go to trap these otherwise ghostly particles. So one of the things that scientists do often is to build these gigantic neutrino detectors either deep underground or actually the biggest neutrino detector in existence today is a cubic kilometer of ice beneath the South Pole. So using the ice itself as the medium with which to detect neutrinos.
Where else can we find these big devices?
Well, the nearest one is not far from here. It's in Sudbury, Ontario.
Who knew?
And it's called the SNOW Lab now, the Sudbury Neutrino Observatory. It's the world's deepest physics lab at the moment, and it's played a pivotal role, in particular in nailing down solar neutrinos. For 30 years, scientists puzzled over the fact that we weren't detecting as many neutrinos as we should have coming from the sun. The sun is powered by nuclear reactions, and you can calculate how many neutrinos that those reactions should produce. Experiments were registering many fewer than expected, and that remained a great embarrassment of 20th century physics. And Sudbury played a key role in solving that mystery. And it turned out the reason that we were measuring many fewer was that these neutrinos actually are kind of like cosmic chameleons. They change flavor. They come in 3 different flavors and they morph among them. We weren't measuring the 2 of the 3 types. So it's something to do with this bizarre chameleon-like characteristics of the neutrino that made them so difficult to understand.
You mentioned a couple of minutes ago that the neutrinos had some exciting news a couple of years ago that they might travel faster than light, essentially proving Einstein wrong.
Which is the reason it got so much coverage, but it turned out to be much ado about a faulty cable.
Ah.
So they do not travel faster than the speed of light, to the best of our knowledge.
So it was wrong.
It was wrong.
Okay, so Einstein's still right. We're still holding on.
Absolutely.
Okay. Yeah. Is there a risk in overstating the importance of a neutrino?
Not in the sense that I think because they're so ubiquitous, but also the reason that they're so exciting and interesting and worth talking about is because they play a starring role in great many sagas unfolding across fundamental physics, cosmology, astronomy, and now even into geology, understanding the internal heat source of the Earth. And someday even in more practical applications like nuclear engineering and perhaps even communications. So they really do span such a wide range of phenomena. Neutrinos have, they could be messengers from the cosmos to us. We could put them to work right here on Earth. And we could use them to learn about the shenanigans of the subatomic realm. So they really are ubiquitous, and they play such an important role. It's hard to overstate their importance, and also just the story is very fascinating, from the initial proposal to the dogged experimentalists who had to work hard to pin them down, and then in the last sort of 10-15 years, the discovery that they come in these 3 flavors and morph among them, scientists call them neutrino oscillations, has really opened up new areas of experimentation.
We're going to talk about some of the hunters, the neutrino hunters, the people that have been involved in this work in a couple of minutes, but this is a key player, as you just said. But in terms of the significance for physics, make the parallel in terms of other scientific discoveries. How important is the neutrino compared to what other scientific discoveries would you say it's on the playing field of?
Oh, that's a tough one, to be honest. So neutrinos, for one thing, the discovery of neutrinos from the sun and from a supernova explosion that was observed in 1987 earned shares of a Nobel Prize in physics for 2 scientists involved. Ray Davis for the discovery of solar neutrinos, and then the leader of the Japanese experiment at Kamioka also shared a piece of it. So that gives you some sense, and there's a lot of interest and expectation, at least in the physics community, that the discovery of neutrino oscillations is also worthy of a Nobel Prize. And if that were to ever pass, Art McDonald, the professor at Queen's, who was the leader of the Sudbury experiment at the time, would be a leading contender.
as a layperson, you care about the stuff. You're an astrophysicist. You care deeply about the neutrino. Do I need to care about the neutrino and its implications?
Well, if you want to know, anything about the universe you live in,
Yes.
if you care about, the fascinating phenomena happening all around you, about the particles that are zipping right through your body, and also, your neutrinos really are messengers to some of the most violent phenomena happening in the universe, like exploding stars, cosmic particle accelerators associated with supermassive black holes. So they really, give us a view of the cosmos that we couldn't get any other way. And that's the reason that I think neutrinos are worthy of your attention.
These things are ubiquitous, but hard to detect. And when you do, what's the price tag? What are we talking about when we're trying to do research into neutrinos?
Well, as I said, the scientists have to be rather clever, and they need rather large contraptions to detect neutrinos. Neutrino physics has really come to the forefront in the last decade, I would argue, and really blossoming on multiple fronts. One of the reasons is that, relatively speaking, relative to the cost of chasing the Higgs boson with the Large Hadron Collider, neutrino physics is significantly cheaper. It's not cheap, but it's much cheaper than building the next energetic particle accelerator, high energy particle accelerator. So that makes it a little bit more appealing, and still neutrinos allow you to explore some of the most fundamental questions about the nature of matter, about the origin and evolution of the universe. For example, how come the universe is dominated by matter and not antimatter? How did that asymmetry come about? We don't know. It's a very profound and difficult question, but neutrinos offer one of the more promising avenues for getting at that difficult question. So there are many, many reasons why neutrinos neutrino chasing has become, if not fashionable, certainly quite an active field.
We've talked many times on this program, had the discussion about governments tightening their belts when it comes to scientific discovery and research. So make the argument that neutrinos are worth their salt in terms of investment.
Well, I mean, neutrinos, alone, I mean, they're just part of our quest to understand the world around us, right? So that's the sense in which investment in neutrino research is worthwhile. To begin with, it's curiosity-driven basic research. It's not, for the most part, done with this sense of developing applications tomorrow. However, there are certainly, as has been the case many, many, many times through history, basic science research ends up leading to practical applications in unexpected ways, and neutrino research is no exception. One of the more promising places where neutrinos may come in handy for down-to-earth use is using neutrino detectors to keep tabs, for example, on nuclear reactors. So right now, international monitors have to do periodic inspections of a nuclear reactor to make sure nothing strange has happened in between. But with a neutrino detector, because anytime you run the nuclear reactor, there are neutrinos coming out, and there's nothing you can then do to hide them. You cannot build walls thick enough to stop them. So that means if you can deploy a neutrino detector nearby, you can continuously keep tabs on the operations of that nuclear reactor, making sure nothing untoward is happening, or the operators of the facility are not getting up to some shenanigan that we should worry about.
So I'm thinking, when I'm hearing you there, I'm thinking of things like the tsunami in Japan, right? When the nuclear reaction at Fukushima. Whatever. Would that kind of, if there was a neutrino technology, could it work in a circumstance?
No, it's more in terms of keeping tabs on the reactors so that people aren't using those reactors to produce fuel for nuclear weapons.
Right.
So that's the way in which...
security application.
It's a security application. It's a peacekeeping application. That's one of the more promising ones, and there's been a number of designs for such a system, and at least one prototype that's been tested in California. So it's closer to real world application than many other aspects of neutrino research. And there are many other ideas floating about. Because neutrinos hardly ever interact with anything, people have suggested you might use neutrino beams to communicate from one side of the Earth to the other by sending a beam right through the Earth instead of having to bounce electromagnetic waves around around the Earth via fiber optic cables or or bouncing them off satellites. So you might gain a few milliseconds advantage in your communications if you could use neutrinos. Now that's a bit far-fetched still, but the point being that anytime you explore the fundamental characteristics of nature, you end up with insights that could lead to practical applications.
Okay, you convinced me these little things are pretty important, but tell me about the people who are doing some of the work. You said they're fascinating characters who are working on neutrinos, so tell me.
There's quite a colorful cast of characters in the book, many of them historical, from Wolfgang Pauli, who was this brash, sharp-witted theorist who had no fear speaking up, even when he was a rather young guy. He came up with this idea of a yet unknown particle, which later came to be called the neutrino, to explain the missing energy during beta decay. When he came up with this solution, he was going through, it was seen as a crisis in physics, but Pauli himself was going through a bit of a personal crisis. His mother had died, and his father remarried very quickly, a woman that Pauli despised. His own marriage was in trouble. His wife was in love with another man and left him eventually, and for this man that Pauli described as a mediocre chemist. So, stinging insult coming from a physicist. And it's in the midst of this that he came up with this proposal that turned out in the long run to be correct. And there are others like Ettore Majorana, an Italian physicist, a reclusive genius who disappeared without a trace at age 32, presumably while taking a boat from Sicily back to Naples, where he had a teaching position. His family never saw him again. His colleagues never heard from him again. And there were many conspiracy theories circulating about his disappearance for many years. People even suggested that the mafia got him, or that he had a crisis of faith and joined a monastery. And it's said that for years there were Majorana sightings in Italy, like the way we talk about Elvis sightings in America, because he became a bit of a cult figure locally.
Neutrino, I don't want to judge it by its name, but it's not the most sexy, exciting. Where did the name come from?
The name was given by Enrico Fermi, who is a leading Italian physicist. It means little neutral one.
Little neutral
one,
okay.
Because the neutrino has no electric charge. It's a neutral particle. The big neutral particle is the neutron. So Fermi gave the name neutrino, the little one, because it's much less massive.
Was it named after him? They called it the neutrino.
He's the one who gave it that name. And by the way, I have a bit of a tenuous connection to Fermi in that he was my academic great-grandfather. One of my PhD advisors had an advisor whose advisor was Fermi. So it's, academics like to play this game of tracing our lineage back to, great names in history.
6 degrees of separation in the scientific world.
Exactly.
You've mentioned a couple of guys. Were any women involved in the discovery of neutrinos?
Well, one of the people who played a key role, as you might expect, is Marie Curie, because when the phenomenon of radioactivity was discovered, she and Piya Curie got into the game and were among the leading scientists at the time, trying to make sense of what's happening during radioactivity. She identified, obviously, 2 new elements that were highly radioactive, and this kind of experimentation is what led to the proposal of a neutrino. And there are a number of others. Emmy Noether was one of the most important mathematicians ever, and she had this insight about a connection between symmetry and conservation. And that insight is becoming very, very important in trying to understand how matter came to dominate over antimatter in the early universe. And of course, today's neutrino physics world has many women several of whom I interviewed for the book and are featured in the book. There are researchers from all over the world. It's very much a global enterprise. From Sudbury here in Ontario to a highway tunnel in Italy to a mine in Japan, to a bay on the South China Sea, and all the way to the South Pole in Antarctica. There are these neutrino experiments dotting the globe, and there are researchers of all ages and from many different countries involved in this quest.
And is it a collaborative experience, or is everyone sort of working in isolation?
It's often very collaborative because many of these experiments are big and they take years to build up and develop and then to collect the data and analyze the data. So it's often collaborative. Of course, there's some competition because there's multiple teams and experiments trying to answer the same question. One of the, as I said, the biggest neutrino observatory in existence today is called IceCube. It's where a group of scientists turned a cubic kilometer of ice a couple of kilometers beneath the South Pole. They basically had to, it's a marvel of extreme engineering. They had to drill deep into the ice, about 2.5 kilometers into the ice, 86 holes into which they lowered these steel cables, each of them carrying basketball-sized optical sensors, 60 of them on each cable. So it's basically a little bit like launching something into space where you lower these cables with these sensors into the ice, and then the ice refreezes, and you never access them again. You just collect the data from them, right? So it's this incredible, they had to kind of develop their own high-pressure hot water drill to be able to drill that deep into the ice. So it's technology as well involved in this rather interesting and fascinating story.
I want you to tell me one more story of the book. It's about Bruno
Pontecorvo.
Pontecorvo. It has some Cold War intrigue attached to it.
Absolutely. So he was another one of Enrico Fermi's students back in Rome. Despite his connection to Fermi and Fermi's major role in the Manhattan Project during the Second World War, for some reason Pontecorvo was not invited to join the Manhattan Project. And there's some suspicion it's because he was known to have leftist political leanings. And he initially immigrated to the United States briefly, and then for several years worked in Ontario at the Chalk River facility. And it's during his time in Ontario, actually, that he wrote a paper that came to be rather insightful and inspired these experimentalists to go chasing the neutrino. Anyway, he moved on from Ontario to Britain, where he worked at an atomic research facility near Harwell. And while there, he and his family, while on holiday on the European continent, disappeared one summer in 1950. And this was, as you might imagine, Cold War tensions were picking up, McCarthyism in the US. Given the kind of atmosphere in which this happened, it made headlines around the world because there was an immediate suspicion whether he had been a spy all along for the Soviet Union, or at least he had maybe taken nuclear secrets with him behind the Iron Curtain. So there was a lot of Cold War intrigue, a lot of speculation, and on the part of actually the United States and the United Kingdom to actually play down his importance a little bit, because they didn't want to be too embarrassed if that were the case. And indeed, he did turn up in Moscow at a press conference a few years later and made a case for why he decided to defect. Though very later in life, much later in life, it's possible he might have come to regret it. Yeah, quite an interesting. Yeah, there's quite an intriguing story.
So you talk. There's a number of key figures going back that we've talked a little bit about. Is there one in particular? When we talk about the neutrino, I say neutrino. You say this person is the most important person to attach to the discovery and the applications of neutrinos?
It's a tough one. I mean, I guess I would say, Pauli was the one who invented the neutrino, even though, he himself was normally he was a very confident, brash kind of person. But a few months after proposing the neutrino, he actually had some self-doubt. He told a visiting friend of his, an astronomer, I've done a terrible thing. I've postulated a particle that cannot be detected. In fact, he went so far as to bet a case of champagne against its experimental discovery. So he was this, person with a brilliant sort of solution, a radical solution. It was radical. It's more radical than we can appreciate right now, because back then only 2 other matter particles were known. To suddenly propose a third one without, direct evidence for it was a big, bold step, and he took it, and it turned out to be right.
I have a question. We're talking about notoriety when it comes to these kinds of things, and you talked about the Nobel Prize in Physics eventually given to a couple of the guys involved in detecting solar neutrinos. This is a team sport, as you said, around the world happening. Do scientists, I don't know, resent it when some other guy who was involved in parts of gets named for the prize, or gets named in discovering things and they don't?
It's certainly a difficult choice often, right? And in particular today, particle physics is done in large teams, large groups of, in collaboration across many countries. So some of these prizes, like the Nobel Prize, has a limit of no more than 3 people can share a prize in a given year. That really kind of maybe doesn't always do justice to that team effort that goes into a major discovery. So it's certainly perhaps a time to take a look at that and see if that makes sense, or whether one should give a prize to the collaboration as a whole, recognize the team as a whole. But of course, in terms of the media and in terms of there's certainly interest in identifying key figures even within a big collaboration that can be spokespeople for that, for that discovery or for that effort. So there's this tension certainly, I think, and perhaps some of the prizes do recognize teams as a whole, but not the Nobel, which still has so much prestige associated with it.
We will see if the neutrino gets the notoriety that you say it so deserves beyond the Big Bang Theory.
Absolutely.
Thank you for coming in today.
Thank you for having me, Piya.
Support Ontario's public television. Donate at tvo.org.